Okay, hello. In this video we're going to do hash tables. So we've already introduced hash tables during class, not in a video. We're going to just refresh some basic terminology, take some notes here in our document that keeps track of things we're supposed to know, and do the hash table code for our words project. Alright, let's review the picture. We have a picture here that's from class. There's a hash table, which is an array. And inside of the array, we have a bunch of spaces where we can put stuff. In this example here, we're putting in numbers. Okay, so we're putting the number 20 and 1 and 3 and 23 and so on. And for a hash table, the basic idea is whatever we're wanting to put in there, we try to map it into the indexes of the array somehow and then put it in. So we'll put that under our basic idea is take the lookup key, whatever it happens to be, whether it's a number or a user ID or a name, and map it into the range of an index of a hash table. A hash table is just an array. Okay, and the goal is to make the mapping behave like it's random. So the different items get spread out roughly evenly. Okay, the reason we want to do this is then to do inserting or looking up in a hash table. We have to compute the whatever this spot is that we're supposed to go to. Once we compute that, then we go there and we find it. So the goal is that basically the running time of doing a lookup here is converting this key into an index. So why, if things are spread out and we don't have collisions, okay, collisions are instances where we have two different keys. Here we have 3 and 23. So if 3 and 23 go into the same index, we call that a collision. However, we take the numbers here and map them into the range on the index. If we get the same value for two of them, we call that a collision, and that's bad. Alright, so if we don't have collisions, and we have the thing spread out, then the time to look up, insert, delete will be basically just the time to do the mapping from key to index. Okay, and the mapping that we do from the key to the index is called a hash function. Map the lookup key into the index. So a standard one, if the lookup key is an integer, then the typical first hash function would be h of, let's say, lookup key, call it k. If k is an integer, h of k might be equal to k mod n, where n is max index in the array. So over here, our n is 10. We have 10 spots. So we call that n is the size of our array. And that's what we're doing on the example here. So we have h of x is x mod 10. When we want to put something new in, we hash it. So let's say that we wanted to put in something new, call it 18. If we wanted to put 18 in here, then it would go here in the spot for 8. because if we're using that as a hash function, that's where it would go. 18 mod 10 is 8. Alright, so the goal is to have a hash function that spreads things out relatively evenly and is fast. If the lookup key, let's say k is a string, then a typical thing to do is something like you view k as a maybe base 256 number and mod n, or something like that. So we somehow view the string as a number and then do mod n. There's other things we could do. You could take the bits and do some ORing and XORing and shifting and whatever. Okay, so that's the basic idea. If we're going to do a lookup, then let's see the algorithm, and I'm going to just say pretty briefly here, so you compute hash function h of k. If we're trying to do a lookup of key k and look at index k in the table t. There's some table t. So this thing here, I'm calling the array or the table t. Okay, and then on an insert, it's going to be basically the same. So we compute hash function h of k and put it in index. So put it in index h of k in table t. The question becomes what we do about collisions. So if we're going to try and put something in and there's already something there, this picture here, we handle collisions by putting a linked list at each index. So at index 3, we don't actually put the number that we want to store, we put a linked list. And most of these linked lists will probably be empty or just one item if things work out nicely. If they don't, we may have more than one item at each index there. So if there's a collision, one thing that we can do is keep a linked list there instead of just putting the number. Okay, and we call this dealing with collisions. That we have different choices, so this is called chaining. So that is each entry in table is a linked list. That's a chain. Okay, another thing that we could do is when we get to a collision, we could actually store the value there, not have linked lists, so we could put the 3 actually in there, put the 15 actually into spot 5, but then if there's a collision, then we would need to look for the next spot. So that's something that we could do. It would actually make the code in the end more complicated. So we're not going to do that in here. That would be called probing. And probing can be done in different ways. So probing means we go to a particular spot. If it's already full, then we probe forward in some way, maybe just by looking at the next item. And the next item, an issue that comes up there is what do you want to delete? Okay, so suppose we had 5 and 15 here. 15 was there first. We come and we put 5 in spot 6 because the 5 was already occupied. Now we delete the 15, and the 5 here is in spot 6, and the index 5 is empty. That's an issue because if we go and do a lookup for 5, we see the spot 5 is empty. We should look forward. So how do we know to look forward? We'd have to adjust things. Alright, so that's another choice on how to deal with collisions. Alright, on our insert then, I'm assuming that we're doing chaining. And so then on a collision, either way, is okay, we do an insert into the linked list at index HOK. So the trade-off here in terms of your understanding is it's a little more abstract because we don't just have an array, we have an array of linked lists. It won't be super complicated in the code, but it is something that we have not just an array, but an array of linked lists. So it's like a data structure, a linked list, inside of another one, which is an array. Okay, that's insert. In delete, our basic algorithm is compute the hash function, h of k, go to linked list at index h of k in the table, and do a linked list delete. Okay, now we need to go back and look at the lookup. Also at the lookup here, since we're doing chaining, all of these we're assuming that we're handling collisions by chaining. So we go to this index and do a linked list lookup. Okay, so for all of these operations, the common theme is we have to compute this h of k, and then we have to go do the linked list function there. If you go back to your linked lists, the running time of the operations is the length of the list. So the basic running time of these hash table functions is we have to compute the hash function, and then we have to deal with a linked list of some size. Okay, so the running time for all of these, just going to put them all together. So the running time of operations is basically order time for h plus length of linked lists. This will be order 1 if things work out well. Okay, so a couple things that we have to do. Keep the hash function h very simple so that it's fast. And we want to make sure most linked lists are short. And one thing that we'll do to try to make sure that happens is have a table size much bigger than the number of items. Maybe twice or 3 times. So we'll have room, a lot more room here than the number of items we're going to use, and hopefully that'll help it be so there aren't too many collisions. Now we're not going to focus on the theory of that, just that's the hope. We'll see how things work out. Okay, so now would be a good time for you to pause and tell yourself again what's the basic idea of a hash table data structure, and how do the basic operations work when we're dealing with collisions by chaining. All right, now we want to go and put this into code. So we're going to go over into our words project. We have a function hash.h that's started. I'm going to have a hash table data structure. And so we'll have something of type hash table t that has, this will be an array, or the table t, and then the size will be maximum index minus 1. All right, let's see, do we have a hash.c? We don't, so we'll go ahead and include this other file. And this is going to need the list hash.h as well because we're going to be using the list function. Okay, let's go ahead and split screen this, and we'll have that's the definition of our hash table data structures. So we basically have an array and then the size of the array. We'll skip the H there. I want to initialize the hash table. So I'm going to have hash table t star init hash. Okay, and I can decide exactly what this means. Basically what I want to do is create an initial array that's empty and that is of some size. Alright, so I'll call this a P for pointer, and I'm going to do a malloc, and I need to create one of these things here. So I'll do size of hash table t, and as always we have to typecast that. Alright, so then inside of P we have a table and a size. I need to pick something for the size. I can either make that a parameter or not. I could just pick something reasonable. We'll make it a parameter. So we'll make this initial size. Okay, so we'll copy that in, assuming that they're giving some reasonable value for that, and then we'll initialize the table. That is, we'll create the space for it first. Anytime we have a pointer, you know that we're going to have a malloc. And what we want to do is the size, the number of items that we just copied in, and then we need to do each of those is going to be a list node t. So I have a choice here. Do I want to actually keep a list node? So list node t is for my linked list. So do I want to actually keep the value 3 there, or do I want to keep a pointer? I could go either way on this, and I just have to be consistent. What I'm going to do is keep a pointer there. So this table is actually going to be a pointer to an array. It's going to be an array of pointers. So I'll do this. And I'll have to typecast that. And this would be a good time. I'm going to go ahead and try to compile. So far, this is the only function that I've worked on, so I'm going to go ahead and comment out the rest of that stuff. Let's see, simple list is the last thing that we had. I'm going to include, let's see, we'll call this simple hash.c. We're also going to include hash.h, and we'll make an update in our make file for this. Another one. So for the hash rule, basically just going to replace everything with hash. This one will need the words file. We're going to need the hash file. We'll actually also need the linked list. we're going to call this simple hash sh. Okay. This isn't going to do anything yet, but I just want to see if this even compiles. So I can make up here now hash. All right, and we see that there's some errors already. So we'll take a look at our hash.h. This is going to be a struct. And that's a warning, and that's okay. So let's go back to hash.h here, and we'll put hash.c on the bottom. Okay, so at least this compiles right now. All right, any of these mallocs, we could have a problem where it returns null. That would be because we're out of memory. It typically would be the only reason the malloc would return null, but we'll fprintf to std error, and malloc failed, we'll just say, and exit. We're practicing good coding about always checking return conditions. All right, if we do have a successful malloc, then this p table will point to a spot in memory that is big enough to have our array there, and we just want to initialize it. If these are supposed to be linked list pointers, what should we initialize them to? And their pointers, the right thing would be null. So we would have for I equals 0, I less than p size, I plus plus, and then p table bracket I equals null. If we want to make sure that we take the pointer stuff before we do the array, then we would do this, and then we would just be ready to return p, which was the pointer to the whole hash table t. All right. Let's try to compile again, just to make sure at least it'll compile. Okay. Now we can work on some of these other functions. Go ahead and do the hash function itself. Okay, so what we're supposed to do here is this is supposed to take the word and produce an index that is in the range to look inside of, so we have our variable t there, so it would be t, it's a pointer which points to table. Okay, so we want to do something that makes an index between, so 0 to t bracket size minus 1, t arrow size minus 1. Okay, so I'm going to have some kind of loop. Let's see. We're going to have some sort of loop here. Int I equals 0, word bracket I is not equal to the null character, I plus plus, and then we're going to do something with word bracket I. And as just a starting point, I'll put a total here, starting off being 1, and so this is the character, I'll say total equals total times the character, but then I'll do mod the maximum size, which I'll save in a variable called n, just so I don't have to keep recomputing it. This is t size. And just to do something else, just to put something in there. There's total, and then I'll return total. So this is just doing some operations. Character, this CH is going to be something between 0 and 255. I have some running total. I multiply by some number, add some other number, and then take a mod. All right, so that'll do something. And we'll see how well it does. But it gives some value that's between 0 and the table size. Go ahead and compile. That's fine. All right, so we want to go up and do the next one. We're going to definitely need the lookup. And we'll see in a second that these are going to be actually really easy functions. Okay, so once we get this one working, I think the others will be pretty easy too. So this is our picture over here. We have some value that we want to look up, some key. Over here we have a word that we want to look up. On this picture on the board we had integers. All right, so we have some new number. We had 18. Maybe we want to look up 18. If we had 18 over here that we wanted to look up. So first we have to compute the hash value for 18, and then we want to look at that linked list. Okay, so the first thing we always have to do is compute the hash value, and I'll call it hash val. Okay, so this is h of t and word. So the hash function depends on the table t. Mostly it just depends on the size of t and also the word that we're looking up. Okay, so once we have the hash value, then I want to look at that particular, so if I hashed 18, my hash value is 8. I want to look at that particular spot in the hash table. And my data structure here, my hash table is t. So I want to look at t. What part of it? Am I looking at the size or the table? I want to look at the table. Okay. And then the part of it that I want to look at is the hash value. Okay. So I want to look there, and I want to treat it like a linked list. So if I go back to my linked list, I already have my linked list written. I can look at list.h. List.h, we have a function called lookup, where we give it the head pointer of a list and a word to look up. Okay, now, what is the type of this? So t is a pointer. We use the arrow to get into the table member of it, and then the table is a star star. If I do bracket hash value, that takes one of the stars off. So we still have one star left. So the type of this thing right here is of type list node t star. So that is the type that's just perfect and ready for lookup list. So we would do list node t star p equals lookup list. Okay, so this thing right here is of type list node t star, and the thing we want to look up is the word. Okay, and what does the lookup list return? It returns either a pointer to the node it finds or null, and we could just return that. So now our hash function, our lookup hash, returns either null or it returns a linked list node where the word is. Okay. All right, let's take a look at the next function, and then we can see what you think. So let me put here, I'll put them both on the same. So we have the lookup and the insert. In the insert, we want to do a similar kind of thing as we did at lookup, is we have to compute the hash value, and then we're dealing with a list. So maybe take a pause and guess about what's the basic structure of this function going to be. What's the first thing that needs to be done? And then if you have an idea there, what's the next thing that needs to be done? All right, the first thing that needs to be done just about always in these hash table things is to figure out which part of the hash table you're supposed to look at. So that's the same. All right, in the lookup, once we had the hash value, then we're doing a linked list operation. It's going to be the same here. Once we have the hash value, we're doing a linked list operation. In this case, it will be an insert. Okay, and we need to make it so that the, so let's see, we'll just copy the same thing we had before and then see if it's going to work. Okay, so we have to make sure that the types match up. The type of this one was a list node t star. The type of this one is a list node t star, but let's check list.h. And the insert there, it has a star star. So it's not just a pointer, but it's an address of a pointer. The reason was because the insert, if it's the root node, it actually needs to change that value. So this is lookup insert. So this is insert list, and we actually need to give it the address of this location because it may be updating that pointer. All right, and it returns a list node t star. So we'll save that and return it in case somebody needs it. Okay. There's one more function that we need before we can try this out, and that's the print. Okay, so just like the other functions, we're going to iterate. So just like the other functions, well, this one's a little bit different. So here we want to look at the entire table. Each individual item there is a list, and we just need to go through all of them. So I will have a int I equals 0, I is less than t size, I plus plus. And then an individual one of those, we have the same thing, t bracket table, arrow table, bracket I, so that would be a particular item in the table, which is a linked list pointer. So we would do a print list, that thing, and then pass the file. Let's just check the list.h. So we give it a pointer and a file. Let's just make sure list.c that the print list handles potentially a null pointer. Looks like it does. Okay, because in the hash table, some of these will be null pointers and those will just be skipped. All right. This we had a, let's see, we had a lookup. This was list. Okay. So we have our, which functions do we have? We have the definition of the hash table, which is just a dynamically allocated array of pointers, and a size of how many are there. Hash function that converts a key, we're using strings, into an index that is 0 to size -1. Initializing the table, lookup, insert, and print. So let's take a look at simple hash. Basically here we just want to look for everywhere that we did list and do table instead. So we'll have, we go split screen and hash.h. So we'll have hash table t star, we'll call it t equals init hash, and we give it some initial size. I'm just going to give it 100,000. In the Shakespeare example, that'll end up being okay, probably. All right, and then in the lookups, we're going to do a lookup hash. We need to make sure that the types work out. So lookup hash, it wants a hash table. I gave it a t, which is a hash table. It returns a list node t. There's a list node t. If it comes back and it's not null, then I can leave it the way it was working on a linked list, that's just fine. Otherwise, I want to insert into the hash table. So that would be insert hash. And I can just give the insert hash. Okay, so I need to give it, actually this will be fine if I make this this does not need to be a star star. Let's make sure what that was on the insert hash, and the way I was using t was like that. Okay, so right, I was not really using it. So the reason there would be a star star is if I was actually going to change t as a pointer, but t as a pointer I'm not doing that. I'm not changing that anywhere here, so we'll leave it like this for now. All right, so we have insert hash, and then down here we would print hash. Not head, but t. All right, let's see. It runs. Let's run sh with our Shakespeare example. And see what the counts look like. So just as we should see counts that the word the was 27,000 and something. As a question for you, what do we expect the order to look like? So is it going to be alphabetical order that gets printed in? Or is it going to be largest counts or lowest counts? Just based on what we're doing with the hash functions. Make a guess. And let's see. So this is not alphabetical order. It is not order by counts. It also is not order by appearance. One of the data structures that we used, we ended up seeing the order that things appeared in the file. So first or last that appeared in the file. Let's see what the is 27,000, and there it is, 20% of the way through the file. Okay, so if the hash table did what it was supposed to, it was supposed to spread out the keys. When I'm mapping these keys in there, the ones I'm using are the words, so the words should be mapped around kind of at random. And if they're mapped around kind of at random, and then when I print them, it should look like it's kind of at random. If I want to give a little bit more information, I could. I'll just put it in here and then take it out. Hash.c, so I'll print here slot %i. Put a/n there. So I'll print that and then print the list. I'll put begin slot and end slot. Maybe we'll make this begin. I'll just leave it like that. So what I should see is these begin and end with linked lists in between them, so I can see what the index was. Okay, so we see at entry 0, there's nothing. So that would be like one of these. Entry 1, there's a word. Entry 2, there's nothing. 3, there's nothing. 4, there's nothing. We could kind of look through here and see how long are these linked lists. So here is a linked list. So linked list at index 140 is of length 1. Here I have a linked list at right index 146 that's of length 2. What about the one that has the? The one that has the has one other word in it. Just sort of look through here. Most of them are 1s or 2s. There's one with 3. There's 3 items there in that linked list. So we'll have a homework assignment. There was, let's see, there was 1, 2, 3, 4, 5, 6. So we'll have a homework assignment to do some looking more at the lengths of the linked list. Comment that out. Alright, so what you want to get away from this is you should have the basic idea for how the hash functions work, a basic understanding of what the running time is supposed to be. You should be able to do this on an example like we've done now in some of the quizzes. And you want to be able to do things to this code. So like the other, like the previous examples, now what if we want to do something a little bit different than just printing this out? All right. Good luck and have fun.